So I put this nice quote up from Lewis Carroll about how important values and utilities are, about where your goal is depends on where you want to get to. Because what we're going to do is we're going to mix up uncertainty and goals and actions now. All right. A few announcements. There's a solution to assignment 3 and assignment 4 is out. At the moment, you should be able to do questions 1, 2, and 3. You'll be able to do questions 4 and 5 on Wednesday, after Wednesday or Friday of this week. And you should also be able to do question 6 in it as well. Okay. Does anyone have any questions about anything? So what we've been doing is we've been talking about probability is measured in terms of, defined in terms of measures over possible worlds. The probability of a proposition is the measure of the sets of worlds in which the proposition is true. Conditioning, we just rule out the worlds that are incompatible with the evidence, and then we renormalize. So that we have these belief networks that are representations of conditional independence. Each variable is independent of the variables that are not descendants of it given its parents. So it's independent of those variables that are not descendants of it given its parents. We did variable elimination. We compute the posterior probability of a variable given evidence by summing out the non-observed, non-query variables. Last time we talked about a causal model predicts the effects of an intervention. Okay, are there any questions about any of this? Any questions? Okay. So let's do a first click of questions. So there's this belief network. Requires which probabilities to be specified? All right, how are we going? People need more time. Oh, you just got here. Anyone need more time? Yeah. Okay, 3, 2, 1. Oop. E, yes. All right, good. This is the one that no one could answer at the end of last class. I think you're just tired, is that right? Or you're sleepy or... So you want to change your answers if I do that? We've done that before, and we end up with this peer pressure. You don't get good independent samples of things because everyone jumps on the most popular, even if it's wrong.
That's what I mean. That's why you should turn off the poll before you show the results.
Oh, you didn't have time to do that. Okay. Oh, okay. I thought you were doing the other way around. Yes, that was a mistake. Okay. So which of the following is not true? All belief networks are causal networks. All causal networks are belief networks. A causal network predicts the effect of an intervention. An intervention changes the value of a variable by some mechanism external to the model. Or E, intervening on a variable affects the descendants of the variable. So we want to know what's not true. All right, how are we going? Does anyone need more time? 3, 2, 1. I'll stop it first. Oh, that's exciting. All right, A is the right answer. Let's. if you intervene on a variable, we only had this downstream one. Remember if we had a variable, a network, what it looks like in here. If we observe a variable, remember, we sort of essentially go up and then down, but we intervene, we only go into affect the direct causes of it. So if we intervene on this, if we intervene on this, we change this one, and these ones down here. It's only a downstream. There's no upstream. Whereas if you do observe this, then you end up with, you do an upstream pass. It's as though you can do an upstream pass and then a downstream pass. So E is not the right answer. B is right. So we have causal networks. So we argued before that causal networks should obey the independence. So remember, belief network is just an independence assumption. And so if you have a causal network and these are the direct causes of it, then you'd expect it to obey the independence assumption. Right? So if these are the direct causes of this variable, then you expect everything else to be, the only way to affect the variable is to affect its direct causes, in which case you'd know these and so you could produce this. So you'd expect causal network to obey the independence assumption of a belief network. And C was just the definition of a causal network. Predicts the effect of an intervention. Any questions about that? What? An intervention, well, that's what it means. An intervention means we're going to change this value of this variable, not by changing this, but by changing something outside, by some other mechanism. So if we have the light switch and the light and the switch, by intervening on the light, we're not changing the switch. We're doing some other way of turning the light on and off. No, it means if I have a switch, the switch, I can't spell, switch, switch, and then the light is on, the switch is up, and the light is on, means when I intervene on this, I'm doing it in some way that doesn't involve turning the switch, actually moving the switch. So I'm going to intervene on this variable. I'm not going to change this one. But I could intervene, I could change the light, turn the light on by putting the switch on and off. But I'm sort of not doing that. I'm turning the light on or off without doing this. Okay? Any other questions? Okay. So this is not about causal networks. Just given an evidence and a query, which variables can be pruned before running variable elimination? Oh, I should start it. Okay, how are we going? Do you need more time? Okay, 3, 2, 1. The answer is D here. Significant number of people said everyone else. You can't, if you're querying this variable, if this is my query variable, if I'm querying this and I observe this, I can't prune all the variables that are not observed or queries. I can't prune this and this because I need to know the probability of this in order to compute the probability of this in order to compute the probability of this in order to compute the probability of this. Right? But I can get rid of this and this and this. I can get rid of all of the variables that are not ancestors. Right, so you get rid of all these variables that are not observed or queries and have no observed or queries descendants. So you can get rid of this and this and this. You can't get rid of any of the other variables in this model. Any other questions about this? Yeah.
So just say, so you've got that observed one on the second level on your drawing up there.
Yes?
What if you observe the other one on the same level? So the second, so not the very top, so up one level.
This one?
Yeah, if you observe the other one there.
This one?
Sorry, you've got your root one and then the two below it. What if you observe both of those? Can you prune the root?
Yes, but I didn't give that rule.
So that's why that E got kind of confusing for me.
Hmm?
Because you could technically prune the root too. Then
Hang on, which one are you saying?
I get where you. Okay.
Oh, he was meant to say none of the variables.
Yeah, okay. But it's kind of like none of the ones that are there really cover everything. But okay, fair enough. I was just double checking that I understood that.
Yeah, you actually can, you can prune everything that's sort of, if you think of this as a graph, these sort of actually end up being just disconnected from this graph. But there's actually a really complicated algorithm I could have told you for pruning things, but I refrained. So if anyone's interested, there's something called deseparation, which tells you exactly which one is works. It actually just follows those rules that we gave before, but it's complicated to explain, and this is simple to explain and use, and this does nearly everything you'd want it to do. Okay, any other questions? Okay. So what we're going to do today, so what we're going to still got to do in the course is we're going to do decision making with uncertainty. So we're going to talk about actions and values and goals where we have uncertainty. We're going to talk about how to go about where these probabilities come from, how to learn probabilities. We're going to talk about probabilities and time. So when we have temporal aspects for example, how you localization for the Google car, how you actually do that is essentially one of the probabilistic models we'll do. And we'll also look at some simple probabilistic models of language. So that's what we're going to do in the next 2 weeks. So first of all, today we're going to start talking about decision making with uncertainty. And so what we're going to do is we're going to model the utility of a problem. So we need some aspect, some analogy for a goal, but it allows for uncertainty. So that's we're going to the model that's called the utility. We're going to model a single-stage decision problem as a decision network. So we're going to model simple single-stage decisions, and we're going to have an algorithm to find the optimal policy for one of these. And so what we're going to do is look at this decision network. And so what we're going to do is we're going to look at the case of, so before we looked at a whole lot of deterministic cases. And now we're going to look at stochastic dynamics. We're going to assume it's partially observable. So we're not going to actually know what's true in the world. We're just going to have a partial observability. We're going to reason in terms of features. We're only going to do finite stage problems. We're not going to have indefinite processes that go on indefinitely. You'll actually cover that if you do 422. And we're going to have these complex preferences, but we're still going to assume perfect rationality, flat, singular agent, knowledge is given, and we're going to reason offline so we can actually work out what the best plan is offline. Okay, so this is where we're going in these dimensions that we looked at. So when we make decisions under uncertainty, it depends on the agent's ability, what options are available to it, what it can do. It depends on the agent's beliefs, the ways the world could be given the agent's knowledge. If you remember at the very, very first lecture, we talked about how it depended on your prior knowledge and your observations. Well, now we know how to combine prior knowledge and observations because we looked at probability and Bayes, and that's what we've been doing the next, is how to combine probability and observations about the world in order to update our knowledge. So it depends here on the beliefs, the ways the world could be given the agent's knowledge, where sensing is going to update our beliefs, and as well as that, the agent's preferences, what the agent wants, and trade-offs when there are risks involved. So there are risks when we don't know what's going to actually happen. We have to take risks. And we're going to do decision theory, which specifies how to trade off desirability and probabilities of possible outcomes for competing actions. That's what we're going to do. So here's the basic outline of decision theory. Is actions of an agent result in outcomes. So we're going to talk about actions of agents. We're going to talk about outcomes of those actions. So actions result in outcomes. Agents have preferences over outcomes. The reason you come to class is because you have a particular outcome you want to achieve. The reason you're going to start walking this way is because you have a particular outcome of you want to get to the coffee shop or something. So that's why you have, and then we have preferences over what we want to do. A rational agent will do the action that has the best outcome for them. So here we're assuming this. We have that we're trying to get outcomes that are best for the agent. However, sometimes the agent doesn't know the outcome of the action, but we still need to compare these actions. So nearly all of the scenarios where we have decision making, we don't know the outcome of our actions, but we still have to act in the world. Agents have to act, so doing nothing is often an action. So doing nothing is often an action. So if you think about sort of a medical doctor, they're going to do something, even if letting you not do anything is an action. They don't know the outcome of all the actions. They don't know what's going to happen if they give you this treatment. But they've still got to act. They've still got to observe the world. We've still got to have these trade-offs. Okay, so this is what we're going to do. So what we're going to do is we're going to introduce this model of essentially adding in decisions into our notion of random variables. We have uncertainty, but now we're going to have decision variables as well. Decision variables are like random variables that an agent gets to choose the value for. So random variables we essentially had probability distributions over, but decision variables we get to choose a value for. And now we have possible worlds like we did before. It now specifies a value for each decision variable and each random variable. So before a possible world specified a value for each random variable, and now we have a possible world for each decision variable as well as each random variable. And before we had a measure of possible worlds that sum to 1, but here we only have for every assignment of values to all the decision variables, we then have the measure of the world satisfies sum to 1. So essentially we get to make decisions, and once we've made our decisions, then the world acts how it's going to act. So that's what's going to happen. So we get to choose variables. We get to choose some variables. There's no probability over them. We just actually get to choose. We get free will. We get choice, and we get to once we've chosen our variables, once we've chosen what to do, then how the world acts is a probability distribution over it. And the probability of a proposition is undefined unless the agent conditions on the value of the decision variables. Right? So if you ask the doctor, what's the probability something's going to happen? Well, it depends on whether you take your medicine. Right? So they're going to tell you if you take your medicine, there's this probability. If you don't, there's some other probability. It doesn't depend. They're not they're assuming you can choose the values of these decision variables. Okay. So here's an example. Here's sort of a simple example. A robot can choose to wear pads to protect itself or not. So it can choose to wear pads. The robot can choose to go a short way past the stairs or a long way that reduces the chance of an accident. So you get two choices. The agent gets two choices. It wears pads, it protects itself. It can either go a short way or the long way, and then it can either have an accident or it doesn't have an accident, but that's not under the control of the agent. So the agent gets to choose whether it wears pads or doesn't wear pads. It gets to choose which way it goes, but then it can have an accident or not. It's not under the choice of the agent. This is what essentially, you think of it as world choosing this. Okay, so this is the example that we're going to use for the first part of today. All right. Any questions about that? Is that clear? Yeah. Yeah, so we're going to use squares as choices the agent gets to make, and circles as choices that we'll do that in a minute, just choices that nature makes.
So the robot knows the possible outcomes, but does it know the probabilities?
Well, in here we're actually going to know, we're going to model because knowing the probabilities of accidents given which way you came. So here with the accident, whether you have an accident is going to depend on whether you go the short way or the long way, but not whether it wears pads, but whether the severity of the accident is going to depend on whether you wear pads or not. So it has all these mixes of things. Any other questions? So here the decision abilities correspond to the decision variable, the choices that it gets to make.
Well, I mean, like if the robot has the ability to walk, would that not be a decision variable?
So when you for more complicated ones, we actually have for every possible decision at every time we model as a decision variable, and so it has to work out where to step at each time. So they're the things it gets to choose. But this one here, it's a very simple example. But normally, every choice that you have to make, should I go left or right, where should I place the next sensor, is a choice the agent makes. But once it's made a choice, then nature there's probabilities are associated with what happens. Okay, so you can steer left, and you might fail to steer left but you get to choose steering left or right. So the squares here, the decision variables, are those that the agent gets to choose, and the circled ones are those that the agent doesn't get to choose. That's what we're doing here. Any other questions? Okay. We'll come back to this example. So in order to formalize this, we're going to talk about something called a lottery. And what's going to happen in a lottery is, because you may not know the outcome of its actions, the agent doesn't necessarily know the outcome of its actions, but only has a probability distribution over the actions. So we might not know about it. We're going to have this lottery we're going to write as this. With probability P1, you get outcome O1. With probability P2, you get outcome O2. And with probability PK, you get outcome OK, where each OI are outcomes and the probabilities are real numbers greater than or equal to 0 that sum to 1. And this specifies that outcome OI occurs with probability PI. So it's just a funny notation for just a choice, a random choice that we're going to use when we define things. So now we're going to talk about what's called a utility. So utility specifies someone's preferences over possible worlds. So this is essentially like the goals we had before, but now we're going to specify utilities. And each possible world has a real valued utility, so it's a property of possible worlds. So each possible world now has this real valued utility that measures how desirable the world is, how much we like this world to be in. And we're going to suppose the best world, there's a best world out of all these worlds, we're going to call best, and it has a utility of 1, and the worst world has a utility of 0. Okay, so that's what we're going to set. Just by definition, we're just going to assign it to 0 and 1. And this world, W, has some utility, means the decision maker. We're going to compare it to a lottery between the best and the worst outcome. So we're going to compare this lottery between, with probability P, I'm going to get the best outcome. With probability 1 minus P, I'm going to get the worst outcome. And I'm going to prefer the outcome W to the lottery if I'm going to prefer W to the lottery hang on, it's the wrong way around. Hang on, wait a minute. I just made it up this morning. You prefer the lottery. This is the wrong way around. You prefer. So essentially, so what happens is that we're going to end up with this. Let's go down here. So we're going to be indifferent between W and the lottery, between picking the best and the worst when P. So we're going to think about we're going to think about having a toss-up between the best and the worst outcome. And at some stage, we're going to change our mind. As P changes, we're going to change our mind between preferring this lottery and the best thing. So we can think about here as P on the x-axis. P on the x-axis, we're going to have this P in this P of best. And now we're going to work out what happens. Do we prefer P with best and 1 minus P, we get the worst outcome. There's this outcome. We get to choose this versus choosing W. So we either get to choose this or this. So if P is 0, what should we choose? For almost all of your W's, what should we choose? Right, for this one here, we should choose W, right? So we're going to choose that for a while. When P is 1, we're going to choose, what are we going to choose? If P is 1, right, this is the best outcome. So we're going to choose the lottery. And so it's going to come like this. And so what happens is when we get up to a place, we're going to flip. So we're going to think about, for each P, we're going to think about how varying this versus this. And as we increase W, all of a sudden we're going to flip. And is this the right way around? You prefer W to the lottery. So this is you prefer W for all P's less than. Oh, I won't change it. Okay. Okay, so you prefer W to the lottery for all P is less than the probability, the utility of the world. So when the probability is less than this, I'm going to prefer the world. Right, when the probability is bigger, I'm going to prefer the lottery. And at this point, this utility of the world, this point here is going to be the utility of the world. Okay, so let's go through this. Let's look at this example. So what's the best outcome here? So what's the best outcome? So W5, so the best outcome, W5, is claimed to be the best outcome. Right, it's going to probably 1. Right, you don't wear pads, you go the short way, you don't have an outcome, everything's nice. What's the worst outcome? What is it? W6? Okay, so you didn't wear pads, you went the long way, you had an accident, so you ended up with severe damage, but you also paid the cost of going the long way. And so now we're going to scale these between this. Right, so W0 is you end up, so now we're going to try and work out where on this scale we're going to put W0. So W0, we wore pads, we went the short way, but we had an accident, but we only had moderate damage, right? So now we're going to somehow think it's down here because we've got to think of this, of some lottery between, because I don't know what's going to happen, so I've got to work out some lottery in here between this W6 and W5. So with some probability I'm going to end up with W5, with some probability I'm going to get W6, and I want to know at which probability I'm indifferent between it when I'm gambling. Right, so I'm going to work out this. So maybe W0 is here. And now we're going to think about, again, we're going to think about, so for W1, we want to think about where on this scale it comes. We wore pads, we went the short way, we didn't have an accident. So where does that come? Yeah. W5 is the best outcome, someone told me.
So what are we hoping for? The one next to the worst, not the one that is closest?
So the best outcome was W5, is that right? Yeah. And the worst outcome is W6. So that's 1 and 0. So for this one here, I'm going to choose some value where I'm going to think about what's the probability. When I choose, this say might be 0.3 or something. So this is, I'm indifferent between this. I'm indifferent between with 0.6 I get W6, and with 0.7, and 0.3 I get W5 and W0. That's what this means. Right, so I get 30% chance of getting the best outcome and a 70% chance of getting, right, so 0.3 times the best outcome and 0.7 times the worst outcome, and I can't decide between that about whether I choose W0 or not, if I had to take risks. because I have to trade, because there's a risk that this is going to happen, there's a risk that this is going to happen, there's a risk that all these things might happen. And now I've got to work out where in my risk assessment I'm going to put this. So think about a doctor prescribing drugs, right? There's a chance you can, one is the chance that one is you live a happy life for the rest of it, 0 is you die. And somehow you've got to trade off. If there's a risk of people dying, you've got to work out how to trade these things off. You've got to work out that, how we're going to spend $1,000. How much of this, there's something called a millimort, which is a 1 in 1,000 chance of dying. You've got to try and work out how much you're prepared to spend in order to reduce your chance by 1 in 1,000 chance. No, I mean that we don't get to choose which one of these happens, but we get to choose which action we do. So imagining that this could happen with some probability, and this could happen with some probability. And now we're going to place this other one and saying, well, where in this risk assessment would we place W0? So, if I could get this, right, somehow this agent's going to think about, well, maybe this is the possible outcome. And which one would I prefer, this or this? Right, and if you choose one up here, it's going to choose the lottery, and it's going to keep going down here until all of a sudden you're going to choose W0 is better than this. So you essentially keep filtering something down here until all of a sudden you flip, which is what this graph here says. All of a sudden you're going to start here, and all of a sudden at some point you're going to flip. You're going to change your mind. So here I'm going to choose the lottery, here I'm going to choose the lottery, here I'm going to choose the lottery. Oh no, here I'm going to change my mind, I'm going to choose W0 everywhere down there. If the risk of this is big enough, then I'd rather have this. If the risk is small, I'd rather have something else. And what's going to happen is this is sort of going to be unit, as though we're going to talk about everything is in terms of this risk of the worst and the best outcome. We're always going to talk about trading everything off in these, medicine they use millimorts, chance of dying, which sounds awful, but it's something that you can actually measure. It's something you can trade everything off. Yeah.
So I think I understand the scale, but I'm having a bit of issue with the notation used on the right side of the board. Could you just elaborate on what that notation really represents?
This is a lottery with 1.5 chance, with probability 1.5. This says with probability 0.3, W5 occurs, and otherwise W6 occurs. That's what this means.
So is that related to the 0.3 that you wrote on the scale?
Right, so P, yes, this is the 0.3. This is the 0.3. This 0.3 here, probably the best, corresponds to this 0.3. So this is why I'm choosing. I get to choose this number. I'm effectively going down, and I decided here that it's going to stop at 0.3. Right, when you do take a risk of, in the assignment, you've got to work out a risk of, how bad is it to get caught cheating? Right? If you cheat, then you're taking a risk about whether I get caught cheating. You've got to work out how many marks is it worth to me, right, to take a risk. So you think about how bad it can be, and you think about how good it is, and then you take risks. And the medical doctor, they think about how bad it can be and how good it is, and they take risks. They've got to choose somewhere in the middle about where they're going to trade things off. And then we're going in the scale, we're then going to place W0 is, so W1's sort of way up here, right? W1's actually pretty good. It has some, so then we're going to place all of these somewhere in here. So we're not willing, it's not worth exactly W5, but it's pretty close, right? Because we're not willing to give it up. We don't want to take much of a risk of getting the worst outcome. And then we're going to scale all of these in between this. Okay, are there any other questions about this? So what we're going to do is we're going to try and, once you do an example, it makes a whole lot of sense. So in the assignment, there's an example of people trading off someone who really wants to get an A and really wants to get an A and is willing to do all sorts of work to get an A, and someone who just wants to pass, then to having different risk assessments. This is non-trivial. When the turn of the century, Time magazine had this thing about what are the greatest inventions of the 20th century, and utility theory, I think, came out as number 3 or 4. So this theory that says that we can really trade off between these lotteries and things because it's sort of the basis of economic decision theory, because you can mix them with probability, and things get to be nice mixes of making decisions. And it's really the basis for all of these decision-making under uncertainty, where we have to actually make decisions. We end up thinking about utilities in terms of lotteries and trading things off because we're worrying about uncertainty because we're taking risks in here. Okay, any other questions? All right, I'll fix these up. Later on, we're going to do utilities can be any real number, and we're just going to scale them to 0 and 1. So often we're actually going to use 100. Often we use 100. Often we're going to multiply all these by 100 and then use 0 to 100. And sometimes we talk about in costs and we end up having negative numbers. But they really mean the same thing. We're just scaling them onto this. And it should become pretty obvious about how that works. Right, because there's no real reason. So we sometimes want to use a different scaling factor to probabilities. Just say them from 0 to 100, and then we talk about percents. And the whole thing doesn't matter here about what else scaling is. Because we're only really going to use one utility value, whereas we're going to multiply lots of probabilities. They sort of have to obey the 0 to 1 rule. But these utilities, we're only going to use one utility model for any decision. And different people can have different utilities. So part of research people are doing, we've been working for, we had some studies where people were working out the wastewater for the new building, the Vanier building, and we had people sitting there and arguing about the utilities or the cost-benefit trade-offs for all these different options for putting wastewater. And then we had people sitting there and arguing about what the utilities should be. So, because this one we could actually argue about what's important and what's not important, and how important is it. We could trade things off and we could put things into decisions. Then we say, if these are your values, here's what decision you should make about the wastewater. Okay, so we're going to do things like that. So the other one is the other thing we need to build this theory is expected value. The expected value of a function of possible worlds is average valued, weighting possible worlds by the probability. So we're going to, if f of w is the value of function f on world w, the expected value is, we're going to write this funny e of f, as we're going to sum over all the worlds, the probability of the world times the f of this world. Right, so if we have, here's the simple example. If we have the roll of a dice, and you get the value on the dice, if it's odd, and you get -1 if it's even, what's the expected value? Right, so you've got these two things. You roll a dice, you get this value on the dice, you get -1 otherwise. What's the expected value? Is this something people know how to compute? Right, you get, right, so it's 1/6 times, it could be a 1, which is you get 1, you get 1/6 times -1 plus 1/6 times 3 plus 1/6 times -1 plus 1/6 times 5 plus 1/6 times -1. Right, so here's all the outcomes. This is all the probabilities of these outcomes. And here's the value of that outcome. Right, so this is what we did. This is the outcome. You get a 1, you get 1, you get a 2 is rolled, you get -1. If 3 is rolled, you get 3. If a 4 is rolled, you get -1. If a 5 is rolled, you get 5, 6. So it's just the probability times utility. And if someone tells us that it's less than 5, if the given the outcome is less than 5, we're going to end up just ruling these two out. And we end up with each of these as a probability a quarter. So we get a quarter times 1 plus a quarter times -1 plus a sixth, a quarter times 3 plus a quarter times -1. Right, so we only look at those worlds where this is true. So that's just expected values is something I think you probably, just the average value weighted by the worlds. Okay, it's I think something you'd probably, all right, so any questions about that? So now let's stick everything together. So we're going to look at first we're going to look at single decisions today, then on Wednesday we're going to look at multiple decisions when we're going to make sequential decisions. So an agent makes all the decisions before acting in this case. And you've got to choose the value for each decision variable is what's going to happen. And we're going to combine all the decision, when we do this theory, we're going to just combine all the decision variables into a single variable D. And then the expected utility of decision D is the expected value of U, where U is the utility function. So U is this function on worlds, is the utility function of the expected utility given this decision. Remember, I only had utility defined when we were actually conditioned on the decision. And the optimal decision is the decision D max, whose expected utility is the maximum. So I'm going to choose the decision D max. I'm going to choose to do D max such that that's the maximum of all of these other values. So I'm going to choose the maximum thing I can do. So I'm going to try and choose the maximum decision I'm going to do. And so then we're going to end up extending our belief networks to include these other things. So we're going to include decision nodes. We're going to use these as rectangles. The agent gets to choose the value of these. The range of these is a set of possible action. We're going to draw this as a rectangle. So we're going to choose, the agent here gets to choose whether it wear pads. It gets to choose which way it goes. And it gets to, then there's an accident here. This says the accident, the probability of the accident only depends on which way you go. But the utility depends on whether you wear pads, which way you go, and whether you have an accident or not. Okay, so we have the utility nodes. Here, the parents are the variables on which the utility depends. I'm going to draw that as a diamond. So we have, so the random variables are those ones we did before. And this explicitly says that which nodes affect the accident. So this says whether you wear pads, whether the agent wears pads or not doesn't affect whether it has an accident. Right? So now we've got to choose a value for wear pads, choose a value for which way, such that we're maximizing this expected utility. And that's what we're going to try and do with these things. So in here we have a directed acyclic graph with three sorts of nodes. There are decision nodes. There are these rectangles. There are random nodes, and there's one utility node. The range for the decision, there's a range for the decision and the utility nodes. There's not a range for the utility node. That's just going to be some real valued number. So there's only going to have one utility node, we're assuming. And for now, we're going to assume that all decision nodes come before all random nodes. Now we have a conditional probability table for each random variable given its parents. We have a utility function, depends on the parents of the utility node. And there are no tables associated with the decision node. So in our tool that we've been playing with, we can just add these in. So we end up where are wear pads, which way, with the utility. we're going to end up with a function here that tells us just this is the same thing we've always had before. It just says which way, whether we go short or long, we have an accident. So if we go the short way, there's a probability of 0.2. And if we go the long way, there's a probability of 0.01. So now we have this, just the normal way we did for Bayes nets. We're now going to extend it to these decision networks. There's the table for the utility, which is just going to be this one down here, the one we drew there. We're going to have the best outcome here was that we didn't have an accident, we went the short way, and we didn't wear pads. The worst outcome is going to be this third one here. We went the long way. We had an accident, we went the long way, and we didn't wear pads. And then we scaled each of those in between there. So there's this one table for this decision node. And there are no tables for decision nodes. Right? We don't get to choose the value of it. There's no table associated with these things. The other thing to notice about this is that we actually have a value for each value for accidents in here. So it just depends on for each way, for each one of the parents, we get to have a distribution over where we had an accident. But the utility node is sort of different from that. There's no distribution over utility. There's just a utility for each value for the parents. So there's just this function that says which way we're going to go. Okay. All right, so now we have this little modeling language. We can model decisions. So now what we'd like to do is we'd like to select values of the decisions in order to work out the expected utility in here. How do we go for time? We've nearly finished. Okay. So what we can do in here is, so one of the things when we solve this, we can do solve this node. So let's just let's do brief. So what we can do is if we viewed this expected utility, we actually end up with computing some average value in here. So the average value is 83. And what it did was it actually assigned a value. So it said when we're wearing pads, it said we should go the short way is the optimal thing in here. It's going to choose a value for the decision node which optimizes it. And it's going to choose the value for whether we wear pads. So the answer here is it's going to wear pads. The optimal decision here is to wear pads, and here and to go. Whoops. So the optimal decision is to wear pads, and we can actually look at the utility. Let's look at the utility function. We get an expected utility. We can look at the probability of an accident like we did before. And we can change our decision. So we could say when we wear pads, we'd like to make it, if I don't wear pads, it's going to change. The expected value is going to be 80.6. So if I change this decision, I'm going to change the utility. Okay, if I change this decision lets me change it. So I can now change it for it to go long, whichever way this other one goes, and again to 79. Right, so if I went, so for each assignment of wearing pads and utility, we have a probability of an accident and the utility changes. And what we're going to do is we're going to try and, the problem now is to choose values for these decision variables that maximizes our expected utility. Okay, so we get to choose these. Right? We get to choose this, which one we do here. And now we're going to, for each of these values, the same our calculus we did before, computes expected values, and want to maximize our decision. So let's stop there.